Hi guys, this is Mrs. Lyons, and this video is going to take us through using the solubility chart to figure out how to write something we're going to call net ionic equations. Net ionic equations are equations that show us just what is happening. Anything that is not reacting, we're going to eliminate. Okay, in order to do that, we have to know how to use the solubility table. Okay, so there are 5 compounds here, and we want to determine if those compounds are soluble or insoluble. Okay, so what you're going to do, almost in every situation, you're going to be looking for the negative ion. Okay, because that's what we have listed here. The one exception is if we see group 1 metal cations, okay, so sodium, lithium, beryllium, or not beryllium, sodium, lithium, potassium, cesium, those elements in group 1, those are always going to be soluble. So potassium here is a group 1 metal, so I know that is going to be water soluble, so I would give it an AQ designation. Okay, magnesium carbonate. So we're going to look for carbonate in our list. So we see carbonate is right here. Carbonates are always insoluble. The only exceptions for this whole list are the group 1 metals and ammonium. Okay, so if I see a carbonate, unless it's with a group 1 metal or ammonium, it's going to be insoluble. So I would designate that with an S for solid. All right, iron 3 oxide. So again, I'm going to find oxide right here. Oxide is insoluble. Iron is not a group 1 metal. Copper 2 nitrate. So nitrate is up here. You will see that nitrate is always soluble. There are no exceptions for these compounds. Okay, so nitrate is going to be aqueous. And then finally, calcium fluoride. So I'm going to look at my list. I'm going to find fluoride. I'm going to go over the exceptions are magnesium, calcium. So calcium sulfide would be a solid. Okay. All right. So now let's talk about what happens in double replacement reactions. Okay. So when we're doing a reaction in aqueous solution, okay, we use something called an ionic equation. And what an ionic equation, how that differs from what we've been using. Ionic equations differ because they show the substances written as ions, okay, not as compounds. So what we are going to look at now are double replacement reactions. That's where we need to use this idea of the net ionic equation, okay? So what we have when we have a double replacement reaction, we also call that a precipitate reaction because we're forming a precipitate, we're forming a solid, all right? So a precipitation reaction is a type of double replacement. All right. What happens is in a precipitation reaction, one of the products is going to be a water insoluble compound or precipitate. Okay. The reactants in a precipitation are usually water soluble. All right. If a cation and an anion come together and they form an insoluble substance, okay, what happens is a precipitate is formed. All right. Now, in order to determine if the precipitate forms or not, we're going to use the solubility table. Okay. And we're going to use the solubility table to write a net ionic equation. Okay, so I'm going to give you the rules, and they're right there in your notes, of the steps we need to take to write a net ionic equation. And then we'll do some examples. All right, so first we have to write a balanced chemical equation like we've been doing. Then we're going to use a solubility chart to determine which of the substances are soluble and which are insoluble. Any soluble substances we're going to split apart into their ions, kind of like we did when we were drawing those pictures in the beakers. Soluble compounds break apart into their ions. And then we don't include the subscripts. We change the subscripts to coefficients to show the number of ions. And then once we've got it all done, we're going to cancel out what we call spectator ions. Those are ions that don't participate in the chemical reaction. And finally, we'll rewrite the equation showing only what is reacting. All right, so let's try an example. All right, so this first example says, write the balanced net ionic equation for the reaction of aqueous barium chloride and sodium sulfate. Okay, to give barium sulfate and sodium chloride. So the first thing we have to do is we have to write an equation. Okay, so I'm just going to write this whole thing out. Barium chloride. We said that those are both aqueous. Both of the reactants are aqueous. All right, barium chloride and sodium sulfate are going to combine to produce barium sulfate plus sodium chloride. Okay, so now that we've got our products, the one thing that we're going to have to do is we're going to have to look at our solubility rules. Okay, and we want to look at our solubility rules for the compounds that we've made. So barium sulfate. So what do we see about sulfates? Sulfates are here. They're soluble except calcium, strontium, barium, and lead. So barium sulfate is going to be a solid. And then sodium chloride, you guys will get better at recognizing this, but sodium's a group 1 metal. All group 1 metals are always aqueous. Okay, so now what we're going to do, we are going to do step 3 up here. We're going to break the aqueous compounds apart into their ions. Okay. Oh, we have to balance first. Let's see. Barium is good. Chlorine, we've got 2 here and only 1 here. So a 2 there. I believe then I am balanced. Okay. So now we're going to break this apart. So barium chloride is aqueous. So I'm going to break this apart into a barium ion plus 2 chlorine ions. Okay, and notice we move the subscript out front to be a coefficient to show how many ions we have. All right, then we're going to have 2 sodium ions plus 1 sulfate ion. Okay, on the product side, barium sulfate is a solid, so it does not break apart. We keep it just like this, BaSO4. All right, and then we're going to break the sodium chloride apart because it's aqueous. So we end up with 2 sodium plus 2 chlorine ions. Okay, so that's our complete ionic equation. Now we need to cross off the spectator ions. Okay, and the spectator ions are ions that appear exactly the same on both sides of our equation. So barium does not appear the same way. Chloride, so here we have 2 chloride ions, over here we have 2 chloride ions, so we're going to cross those off. Those are what we call spectator ions. They don't participate in the reaction. All right, we have 2 sodium ions. Here we have 2 sodium ions. So we're going to cross those off because they don't do anything. They just kind of watch. And then finally, we've got sulfate here and sulfate here. So the barium and the sulfate we're going to leave in the reaction, okay, because that's what is happening. So I would write my total net ionic equation as Ba plus 2 plus SO4 minus 2 produces BaSO4 solid. All right, so let's try another example. All right, let's try this one. Write a balanced net ionic equation for a reaction of solid lead 2 hydroxide and hydrochloric acid. All right, so what we need to do first is we need to, now this one we actually have to predict our products. So it doesn't just give us the products, so we're going to have to come up with those. All right, so we'll look here, give myself a little bit of extra room. All right, so our reactants are solid lead 2 hydroxide. All right, so let's see, that would be lead 2 is plus 2, hydroxide is OH minus 1. All right, so we start out with PbOH2. All right, and that it says is a solid. And then we're going to react that with hydrochloric acid. Remember, when we have an acid, hydro tells us it's just the element. So chlorine has a -1 charge, so this is going to have 1 hydrogen, 1 chlorine. HCl is hydrochloric acid. That is soluble. Okay. Now we need to predict our products here. Okay. So remember, when we do this, the metal, and in this case the hydrogen, are going to stay the first element. So I'm going to combine, I'm going to switch places. The hydroxide and the chlorine are going to switch places. So I'll end up with PbCl. All right, and here the lead we know is a +2, so it's going to be PbCl2 plus HOH, which is water. All right, now this is kind of an interesting thing because we don't really form, well, let's look and see what we form. All right, but we're starting with a solid and an aqueous compound. So let's look at our solubility rules and see what we have. All right, so we've got lead chloride. So if I look on my solubility table for chlorine, okay, it's soluble unless it's with lead. Okay, so that tells me that my lead chloride is a solid. And then when we make water, okay, when we do a reaction and one of the products is water, we are going to write that as a liquid, okay, not aqueous, because water is not dissolved in itself, okay. And anytime we form water in a reaction, that's also going to be something that we don't eliminate in the process, okay. So let's look at this. If we break this apart into our pieces, okay, so we've got lead hydroxide, that's a solid. So I'm not going to do anything with it. It's just going to be PbOH parentheses 2 solid. All right. Then we're going to have hydrogen and chlorine. So hydrogen, one of them. Since it's an ion, we do not consider Hobrofinkel. Okay, we don't care about the diatomic elements here. Plus 1 chlorine. minus 1. All right, and then we're going to produce PbCl2 as a solid. And oh, you know what? We did not balance this. So we'll balance this in just a minute. And water. So H2O liquid. Okay. I need to balance this. So I've got 2 chlorine. If I put a 2 here, that gives me 2 hydrogen and 2 OHs. So I can put a 2 here also. All right. So now let's look at this. Is there anything in this equation that is seen only on one side? And as we look at it, the answer there is there are no spectator atoms or ions. Okay, so this is the total equation and the net ionic equation, okay, because there's nothing to cancel out in that. All right, so that one's a little bit weird, but it's good to see some exceptions. All right, let's do one more together, and then I'll let you guys work on some practice. All right, so we want to write the net ionic equation for sodium phosphate and potassium carbonate. All right, so let's look at this. All right, so we've got sodium phosphate and potassium carbonate. So let's go with sodium phosphate is going to be Na3PO4. That's aqueous. All right. And then we have potassium carbonate. That's going to be K2CO3, also aqueous. All right. And then we got to figure out what those are going to combine to make. So we know we're going to combine opposite parts. So we've got sodium carbonate. So that would be Na2CO3 plus potassium phosphate, K3PO4. All right, let's balance this. All right, so here I have 3 sodium, here I only have 2, so I'm going to make that 6. I want to get 6 sodium, so a 3 there, a 2 there. Let's see, I have 2 potassium here, 3 over here, so that's also going to be finding the common denominator or the common factor of 6. All right, so that would be our balanced equation. Now let's look at the solubility table. All right, well, I guess let's just go ahead and write the complete ionic equation. All right, so we know that the reactants are water soluble, which means they break apart into ions. So I'm going to have 2 times 3, I'm going to have 6 sodium ions plus 2 phosphate ions plus 6 potassium ions and 3 carbonate ions. And I'm going to make my products are going to be 6. Oh, we got to look at solubility. Hold on. So sodium carbonate. So this is a carbonate, okay? Carbonates are always insoluble unless it's with a group 1 metal. Sodium's a group 1 metal, so this is going to be an aqueous water-soluble compound. So we end up with 6 sodium ions and 3 carbonate ions. All right. Now, potassium phosphate. Let's look. Phosphates are always insoluble unless they're with a group 1 metal. Well, guess what? Potassium's a group 1 metal. So I'm going to write this out. I'm going to have 6 potassium ions and 2, so this is aqueous, phosphate ions. Oops. Now, if you look at this, okay, what happens is if you compare, you have all, so this would be the complete ionic equation, but let's just look if we were to cross off spectator ions. We would cross off sodium, we would cross off 2-phosphate, we would cross off 6-potassium, we would cross off 3-carbonate. So our net ionic equation demonstrates how we get no reaction. Okay, no reaction means that all of the ions, none of them combine to make something insoluble. Okay, so that's what we're looking at there. So that was 3 examples. So just a couple of points as we wind up with this lesson. Solubility, important things. All right, always check the solubility table to decide if a substance will be aqueous or solid. Any substance other than water-soluble substances will not break up into ions and will therefore be labeled with symbols SLG. For our purposes, acids are always considered to be aqueous. No reaction will occur if 2 aqueous substances are produced. And finally, a reaction will occur if a new solid, liquid, or gas is produced. Okay, so that was a quick run through of net ionic equations. I hope that was helpful. Take care. I will see you in class.